Now that we are able to balance the redox reactions, we will take a look at two different electrochemical cells, which are the voltaic cells, or sometimes it is also called the galvanic cells, and the other one is the electrolytic cells. So in this case, we can see the cell diagram. So this thing is called as cell diagram for a voltaic cells. First up, we have several components in the voltaic cells. We have what we call the electrodes. So normally it's in solid form like this, made of metals. Could be copper or silver or inert metals like platinum, or also other metals depending on the reactions that we have. And next we have the solution over here that we call as the electrolyte. So you have electrode, which is the solid, and then you have the solution, which is the electrolytes. In this case, we have two of them. So we have Cu2 plus and Ag plus, and it's normally, of course, in the ionized form, so the salt form. So you can have, for instance, here, copper nitrate, and this one, silver nitrate. So what will happen is, of course, transfer of electrons. So one of them will undergo oxidation, and the other one will undergo reduction. We will get to that in a bit. Another component that we can see is something like a lamp, or a voltmeter that will read the voltage difference between these two electrodes. In principle, voltaic cells will generate electricity from chemical reactions in which the process will occur spontaneously, mostly. Yeah. And because we have one side being oxidized and the other side being reduced, at some point, we will have an imbalance of charges between these two chambers. Therefore, we need to balance the charges using this one that is illustrated in green, that what we call as a salt bridge. So whenever you have two different chambers connected, we need a salt bridge. The salt bridge will create a closed loop of electricity so that electron will flow around this particular cell. And also, as I mentioned before, it will help balancing the charges between these two chambers. The example of voltaic cell is a battery on usage, or other example would be fuel cells that also generate a lot of attention lately as a source of energy. So in this case, you have chemical reactions, and the chemical reactions will produce energy in the form of electricity. We have two different electrodes. One we call as cathode. The cathode will have a positive charge, or the positive pole. And the other electrode we call the anode, and for voltaic or galvanic cells, the anode will have a negative charge. The second electrochemical cells we call the electrolytic cells, or the process itself is called the electrolysis. Similarly, we'll have electrodes, so solid form like this, and it would also have electrolytes, which is the solution with ions. Now in this case, it is the reverse of the voltaic cells, where we generate chemical reactions by hooking them up to a power source or electricity. So in this case, we use electricity to perform non-spontaneous chemical reactions. So normally, the telling difference between these two cells is the electrolytic ones will require a power source. So as you can see, it is hooked up to a power source. So the reaction normally is not spontaneous, but instead, because it is connected to a power source, you are giving energy to the system so that the reaction will occur and become spontaneous. The example for electrolytic cells are battery being recharged. So if you have a rechargeable battery, just like what you have in your phone, when the battery is on use, so they produce electricity, you can work on your phone or use your phone for whatever you want. That means you are using the battery in voltaic cells mode. However, after a day or even less than that, you would need to recharge your phone, and then upon recharging, the battery becomes an electrolytic cells, because now you hook up your phone into a power source or power outlet, and then the reactions will happen in such a way that the battery will become recharged again for another use in the next day. Another example is water electrolysis or metal electrolysis, for instance, in what we call the electroplating, when you try to form a thin layer of metals in one of the electrodes. We will discuss about electrolytic cells in a bit. So those are the difference between these two cells, but there is also an important similarity between these two cells, and that is this one. Anode is always the place for oxidation, while cathode is always the place for reduction, no matter whether you are talking about voltaic cells or if you are talking about electrolytic cells. Therefore, because electron comes from anode, because oxidation again is a release process of electron, so the electron will flow from where it comes from, so the anode, to the cathode. So current, or I in ampere, it will flow otherwise. So always from cathode to anode. Although in voltaic cells, the cathode is positive, anode is negative, and in electrolytic cells, it is the reverse. Cathode is negative and anode is positive. Cathode is always the place for reduction, and anode is always the place for oxidation. You need to remember that before we move to other topics. So I've mentioned before that this is called the cell diagram. To ease the illustration of this diagram, so we don't have to draw them each time, we recognize something that we call as the cell notation. So cell notation is how we try to represent the voltaic cells that we have. And normally we write it down as anode and then cathode. These two vertical lines is a symbol for the salt bridge. So suppose we have this following reaction where we have the two half cells. So during the balancing of the redox reactions, we recognize two half reactions. So one oxidation and the other one is reduction. In this case, we have two half cells. Oxidation half cells and, of course, reduction half cell. For instance, for the oxidation, we have the following reaction of Fe becoming Fe2 plus, of course, releasing 2 electrons. For the reduction, we will have the ion of sulfur receiving electrons and then forming solid Ag. So this one is solid aqueous. Okay, so say these are the half cells that we have. If we have to draw the cell diagram for this, and then of course we will draw two different chambers and then different electrolytes. One will contain Fe2 plus, other one will contain Ag plus. We also have two electrodes. So over here, for instance, a lamp, it will light up a lamp. Here we have Fe solid, here we have Ag solid, and don't forget to close this electricity loop, and to balance the charge, we will have a salt bridge. Salt bridge is normally made of soluble salt. So like KCl, NaCl, and so on. Okay, so this is what we call again as the cell diagram. Now, we can also represent this particular cell in a form of cell notation. So we start with anode, and then the salt bridge, and then the cathode. So how do we write it down? Let's start with anode. In anode, we have electron release from Fe solid to Fe2+. We can write down the phase over here. This is solid and this one is aqueous. Whenever we change phase from a solid to aqueous, we would have to write down a vertical line, but only one in this case. In writing down the cell notation, first we write down the anode and then the cathode. And they should be separated by a salt bridge, which is represented as two lines, two vertical lines like this. While upon changing phase, for instance from solid to aqueous system, we would have to draw one vertical line. So this is the anode where we have oxidation reaction from Fe solid, releasing electron to form Fe2+ aqueous. And then the salt bridge, and then the cathode, which is the solution first, so Ag+ aqueous, and then one line to separate the phase change, then the Ag solid. So whenever you see this cell notation, that means this cell diagram, where you have Fe and Fe2+ and Ag and Ag+ hooked up together like this using a salt bridge and a closed loop, where the Fe will release electrons and the released electrons will be received by the Ag+, while the Ag+ will become Ag. So now hopefully you can also understand the use of salt bridge. In this particular chamber, or let's call this the left chamber, you will continue producing Fe2+. So you will have extra positive charge as the time goes by. While on the right chamber, you will continue producing Ag from Ag+. So as the time goes by, you will reduce and reduce the Ag+ amount further. So here you are lacking the positive charge. So left side you have extra positive charge, right side you have lacking of positive charge. So whenever you have soluble salt, in this case for instance KCl, the place where you are having too many positive charges will be balanced by negative charge. So say in this case we have KCl, the K+ from the soluble salts in the salt bridge will go to this area because now it is lacking positive charge as the Ag+ is being converted to Ag. And the negative one, which is for instance Cl-, so we have a KCl salt bridge. The Cl- will flow from this salt bridge into this solution because this solution is now having too many positive charges because it keeps making Fe2+. So that's how the salt bridge balances the reactions.